Hello, chemistry students. Today we're going to determine the polarity of a molecule. But first, let's talk a little bit about the differences between polar molecules and nonpolar molecules. Polar molecules have a separation of positive and negative charges. This is going to happen when you have a very electronegative atom and a lesser electronegative atom that are bonded together in a molecule. And what happens is that the more electronegative atom is going to pull the electrons toward it. That leaves the less electronegative atom more positive, and it makes the more electronegative atom more negative because electrons have a negative charge. In a nonpolar molecule, electrons are shared equally between atoms. So in nonpolar molecules, you have atoms that have relatively the same electronegativity value. So one doesn't pull electrons closer to it more than the other one does. So they're going to share equally. And I think I just want to add here that there is an unequal sharing of electrons. So electrons in polar molecules are still being shared, but the electrons are going to spend more time around the more electronegative atom and less time around the less electronegative atom. All right, so the two tables that I have here are going to help us to determine what type of bond, nonpolar covalent, polar covalent, or ionic, exists between two different atoms. And as you can see, the title of my first table is electronegativity values. And I just have, I pulled out a couple of elements and I put their electronegativity values here. In order to determine whether a bond in between two of these atoms is nonpolar, polar, or ionic, I just have to subtract their electronegativity values. So if I wanted to determine what type of bond exists between an oxygen atom and a nitrogen atom, all that I have to do is subtract their two electronegativity values. So 3.44 minus 3.04 is going to give me an electronegativity difference of 0.40. Since 0.4 is less than 0.5, that means that a bond between a nitrogen atom and an oxygen atom would be nonpolar covalent. Now, I just want to make sure that you understand that the electronegativity difference value, like this answer here, it always has to be positive. So even if you put into your calculator 3.04 minus 3.44, just take away the negative sign and you'll have your answer. So your electronegativity difference must always be a positive number. So that's how you use these two charts. And I wanted to just bring that up because using them is one of our steps in order to determine whether a molecule is polar or nonpolar. So the steps in how to do this are outlined here. And number one, you have to draw the electron dot diagram. And remember, if you need to, use your VSEPR molecular geometry chart in order to draw your electron dot diagram appropriately. The shape matters. Number two, you have to determine, are the bonds within the molecule polar or nonpolar? And it says use the charts, and the charts that I'm talking about are the two that are up here that I just explained. All right. Number three, draw partial charges according to the electronegativities of the atoms. Well, by partial charges, I just mean that you need to draw these little symbols. So this symbol means partial negative, and the other one would be partial positive. All right. So let me show you how that works. Let's say that I have a molecule that is forming between hydrogen and fluorine, so H and F. And I draw my electron dot diagram, and I get my electron dot diagram to look like so. Well, I need to first know if this bond is polar or nonpolar, so I'm going to subtract 2.1 and 3.98. And when I subtract those two, and I put my electronegativity difference in absolute value bars, what I get is 1.88. Well, that is a polar covalent bond because this answer falls in between 0.5 and 2.1. Since it's a polar covalent bond, let's go back up to my polar molecule. Since it's polar covalent, it means that we have an unequal sharing of electrons. And what this means is that my fluorine, having the greater electronegativity number or value, is going to have a partial negative charge, while my hydrogen, having the lower electronegativity, has a partial positive charge. So what this means, and let me erase some of these straight lines, what this means is that my electrons are going to be attracted towards my fluorine atom. My electrons are going to spend more time around fluorine than around hydrogen. And so that's what these charges mean. Now, I can't just put positive and negative, and the reason why is because if you just have a straight positive and a straight negative, that just means that hydrogen donated or transferred its electrons to fluorine, and that's not at all what's happening here. Hydrogen hasn't given up its electrons. It's just sharing them. Hydrogen's electrons spend more time around fluorine and some of their time around hydrogen. They're still sharing, and that's why we have to use these symbols, partial positive and partial negative. All right, so number 4 says, if polar, you can draw a line through the molecule that separates all partial negatives from all partial positives. Well, if we take a look at our hydrogen fluoride molecule that I drew up at the top here, if I can separate my partial positive from my partial negative by drawing a line right through the center of my molecule. And now I have my partial positive separated from my partial negative. And since I'm able to do that, this molecule is polar. What we're doing here is we are determining the symmetry of our molecule. My charges are asymmetrical. I have all the positive on one side, I have all the negative on the other, and so this would be an example of a polar molecule. Okay, so let's do another example. Let's do an example with water. So my formula for water is H2O, and as I draw out my electron dot diagram, like we did in class, remember your Vesper theory, water has a bent shape. So my water molecule looks like this. So I've already done step 1, draw the electron dot diagram. Step number 2, we need to figure out if the bonds in the molecule are polar or nonpolar. So I'm talking about this line and that line. Are those bonds polar or nonpolar? In order to determine that, I need to figure out my electronegativity difference between hydrogen and oxygen. So if I take a look at my table, my electronegativity value for hydrogen is 2.1. So my hydrogen here is 2.1. And my electronegativity value for oxygen is 3.44. Now, when I subtract them, so 3.44 minus 2.1, I get an electronegativity difference of 1.24. So now I'm going to take a look at my electronegativity difference chart, and I can see that 1.24 falls in the polar covalent area. And what this means then is that my electrons are going to be drawn toward the more electronegative atom. And in this example, my more electronegative atom is oxygen. How do I know that? Because 3.44 is greater than 2.1. So I'm going to draw my partial negative up by the oxygen, and I'm going to draw my partial positive down here by my hydrogen. Well, what about my other bond? Well, because I'm dealing with the same two atoms, I'm going to get the same result. This bond also is polar. So my electrons are going to be more attracted to this oxygen than they are to this hydrogen. So I'm going to go ahead and put my partial negative and partial positive like so. Okay, so I've already done number 2, and I've already done number 3, and now I have to take a look at number 4. If polar, you could draw a line through the molecule that separates all partial negatives from all partial positives. If I draw a line right through the center, I have all of my negatives on top, and I've got all of my positives on the bottom. Therefore, water is a polar molecule because I'm able to separate the partial charges. All right, now we're going to do one last example here, and let's do CO2, which is carbon dioxide. All right, so there's my molecule, and step number 1 says, draw the electron dot diagram. So I've got my carbon in the middle. I'm going to have my 2 oxygens on either side. Now notice that this is not a bent molecule. It's got 3 atoms like water, but the difference between carbon dioxide and water is that my carbon, which is in the center of the molecule, has no unshared pairs around that central atom. Water did, and that's what caused it to be bent. But CO2 is linear triatomic. It's in a straight line because we do not have any unshared pairs around that central atom. Okay, so I drew the electron dot diagram. Next, are the bonds within the molecule polar or nonpolar? Now, I recognize that we have double bonds here, but it doesn't mean that you have to do the calculation twice. It doesn't mean that you have to multiply by 2. None of that. All that you're doing is you're subtracting the electronegativity value of carbon, which is 2.55. I'm just going to write it here, from oxygen, which is 3.44. So to figure out if this bond is polar or nonpolar, I just have to subtract these 2 numbers from each other. And when I do, I get the electronegativity difference of 0.89. If I refer back to my electronegativity difference chart, 0.89 makes this bond between carbon and oxygen a polar covalent bond. Since it's polar, we have a separation of charge, and I need to assign my partial negatives and my partial positives. Because oxygen has a greater electronegativity value, oxygen will have a partial negative charge, while carbon will retain a partial positive charge. So this bond is polar. Now, what about my other bond. Well, once again, just like with water, I'm dealing with the same atoms, so I'm going to end up with the same result. So once again, my carbon is going to have a partial positive, and my oxygen is going to have a partial negative charge. And again, that's because this oxygen has a greater electronegativity value of 3.44. And so if you have a polar bond, you have to draw your partial negatives and positives. If your bonds are not polar, then you don't need to draw your negatives and positives. I'll get to an example of that after this. Let's finish this one though. I've already determined if the bonds within the molecule are polar or not. I drew my partial charges, and now what I need to do is I need to determine whether or not I can draw a line that separates all of the positives from all of the negatives. Well, let's draw a vertical line because that's what I did in one of the other examples. But if I do that, I've got positives, like I'm going right through my positives. I've got a mix, right? I've got positive and negative on one side of the line. I've got positive and negative on the other side of the line. So that doesn't work. And I can't draw a line like this. That doesn't make any sense. I can't bisect my atoms like that. And so my conclusion is that this is a non-polar molecule because I am not able to draw a line to separate all the positives from all the negatives. So, and even if I did, let's just look at this vertical line again. I've got negatives on both sides. I haven't separated the charges. I would have to have all the negatives on one side and all the positives on the other, and I don't. So carbon dioxide, even though it has polar bonds, as a whole, the whole molecule is non-polar. My big takeaway for you for this example is that shape matters. So I can have polar bonds in a molecule, but if its shape allows it to be nonpolar, then it's going to end up being nonpolar if you don't have if you have symmetry. So if you've got symmetry, then you've got a nonpolar molecule. All right. Okay, so let's just do one more example here. We're going to use an oxygen molecule as the example. Step number 1, draw the electron dot diagram. There we go. Step number 2 is this bond in between my two atoms, polar or nonpolar. Well, let's take a look. Oxygen is 3.44. Each of them is. And when I subtract them, I get 0. Since 0 is less than 2.5, I have a nonpolar covalent bond. Since my bond is nonpolar, I cannot assign partial negative or partial positive charges. Because in a nonpolar bond, electrons are shared equally. You don't have a separation of charge because one atom pulls the electrons away. So if you have a nonpolar bond, you cannot assign partial negative or partial positive charges. So I'm done. I have no partial negative or partial positives to even separate, and so number 4 is kind of a moot issue. And what this means is that oxygen is a non-polar molecule. All right, everyone, thanks for watching. I hope you learned a lot. Good luck on your homework. Talk in class. Bye-bye.